All right, so get ready for this deep dive into binary search algorithms. You've sent over a ton of notes and code, and I'm really excited to get into it.
It's a really fun one. And you probably use it way more than you think you do.
Really? I kind of just figured it was one of those things, for coding interviews and like computer sciencey stuff.
Oh, no, not at all. But before we get into all that, let's maybe start with what a binary search algorithm, even IAS.
Okay, yeah, that's a good point. From what I've been reading, it's like a way to find stuff within a set of data a lot faster than just checking each item like one by one. Sort of like if you were trying to find a word in a dictionary, you wouldn't start at A and flip through every single page, right?
Exactly. Yeah, you'd open the dictionary up somewhere in the middle and then see if your word comes before or after the words on that page. And then boom,
Yeah.
you've just eliminated half the dictionary in one go.
Yeah.
Binary search is basically doing that same thing, but with data.
So it's all about efficiency. But in my notes, I also saw something about the data needing to be sorted. Why is that so important?
That's the key. It's like, imagine if all the words in a dictionary were just completely randomized, like flipping to a random page in the middle wouldn't tell you anything helpful. Binary search works by splitting the search interval in half over and over and over again, but that only works if the data is ordered.
Okay, that makes sense. So wouldn't sorting all that data first, like, take a lot of time? Is binary search always going to be the best way to go?
That is a great question. And yeah, sorting does take time.
Yeah.
And there are for sure times when other search algorithms are going to be a better choice, especially if you're only searching a handful of times. But if you're doing a ton of searches within a huge data set, the time you save with binary search is really going to add up.
So it's kind of a trade-off. You spend a bit of time up front to get everything sorted, but then you get all those super fast searches later on.
Exactly. It's like, organizing your tools in a toolbox. Takes a little effort to set it up, but it saves you a ton of time when you need that one specific wrench.
I like that. Now, you mentioned coding interviews. I also saw some tips in the notes here about binary search questions during those interviews.
Yes. The big thing is to really, really understand the input, the output you're going for, and any constraints of the problem before you write a single line of code.
So it's not just about coding, it's about understanding the whole problem first.
Yeah, exactly. And you should talk through your approach with the interviewer. They want to see how you think, not just the code you end up with. Think out loud while you're coding, and don't forget to test everything.
Seems like communication is just as important as the code itself in these scenarios. Now, I'm also seeing a bunch of Python code examples in these materials. So we maybe walk through a few of them
Yeah.
to see how binary search actually works, in practice.
Yeah, definitely. Let's start with problem 704. This one's about searching in a sorted array that we know the size of. You can think of an array like a numbered list of items.
Okay, yeah, I can picture that. So what's the code doing to find something specific in that numbered list?
Basically, the code sets up these two pointers called start and end, and they mark the beginning and end of the array. And then it goes into this loop where it calculates the midpoint of the array.
So it's finding the middle item in the list.
Yeah, exactly. Then it compares the value at that midpoint with the target value that you're trying to find.
Okay, so what happens if the target value is bigger than the midpoint value?
If the target's bigger, we know we don't need anything to the left of the midpoint anymore. So we move the start pointer over to the midpoint, +1. We're basically throwing out that whole left half of the array.
And if the target is smaller than the midpoint?
We do the opposite. We move the end pointer to the midpoint, so we get rid of the right half.
So each step, you're basically cutting the search area in half.
Exactly. And we just repeat this until we either find what we're looking for or the start and end pointers meet up, which means the target's not in there.
Pretty clever. The code actually looks surprisingly simple for something that seems so powerful. Now, there's also problem 702. This one seems to be about searching where we don't know how big the array is ahead of time. How can you even do a binary search if you don't know where the array ends?
That's where things get kind of interesting. We use something called a reader interface.
I don't think I've heard of that. What is a reader interface?
So basically, it lets us check what the value is at any given spot or index in the array without knowing the total size. Imagine having a really long list, but you can only see one item at a time, kind of like through a little window. You can use the reader to ask, okay, what's at position 5? What's at position 10? And so on.
Okay, I think I get it. So how do we actually use that reader to do a binary search?
The solution here is to start with a small search range. Let's say from index 0 to 1, and then it just keeps doubling that range, so 0 to 3, then 0 to 7, and so on, until it finds a value that's bigger than our target. That value basically becomes the new end pointer.
Ah, so it's like expanding the search area until you hit a wall.
Exactly. Once we've got that boundary, we can just do a normal binary search within that range, just like we did in problem 704.
So even without knowing the size, we can still use binary search. That's amazing. Now, I'm also seeing problem 74 here, which is about searching in a 2D matrix. Can you even do a binary search in 2 dimensions?
Absolutely. Remember how we talked about an array being like a numbered list? Well, a 2D matrix is kind of like a grid of numbers with rows and columns.
Right, like a spreadsheet or a table. How do you even apply binary search to a grid, though?
The trick is to think of the 2D matrix as one long sorted array. Even though visually it's laid out differently, we could use a bit of math to convert the row and column, the indices of the matrix, into a matching index in a virtual 1D array.
So you're basically turning the whole grid into a straight line.
Exactly. And once we have that virtual 1D array, it's back to our regular binary search.
I don't like folding up a map into a single strip and then searching along it. I'm really starting to see how useful binary search can be. It's not just for simple lists, it can work with all sorts of complex data too.
Exactly. And there's even more to explore, too. Problem 240, for example, deals with a 2D matrix that has, like, sorted rows A and D columns. It uses an even more efficient diagonal search approach. But I think that's a perfect topic to pick up in the next part of our deep dive.
Ooh, a good cliffhanger. We've covered a lot already, but I'm ready to hear more about these variations and see, like, where else this amazing algorithm shows up in the real world.
Okay, welcome back. So last time we were looking at how binary search works in different kinds of arrays, even when you don't know the size ahead of time. I gotta say, it's already pretty mind-blowing how efficient this algorithm can be.
Oh yeah, we're just getting started. There's like a whole world of variations on that basic binary search idea that we can use to solve even more specific problems.
That's what I'm really curious about. My notes here mention something about finding the first and last occurrences of a target element in a sorted array. That seems kind of tricky. Wouldn't the regular binary search just stop as soon as it finds any instance of the target? Yeah, you're absolutely right. If we just want to know if something's there, stopping at the first match is totally fine. But sometimes you need to know the boundaries, like where that target starts and ends within the data. And that's where these variations come in handy.
So it's like instead of just stumbling upon one tree in a forest, we're figuring out where the whole forest begins and ends.
Exactly. Problem 34 in your notes is all about this. Let's say you've got a sorted list with duplicates, and you want to find the positions of both the first A and D last occurrence of a specific value.
Okay, yeah, I can see how that would be useful. So how do we actually change the binary search to make that happen?
The main logic is pretty similar, but there's one big difference. When we find the target value, we don't just stop and call it a day. We keep searching.
But wouldn't that just keep finding the same value over and over?
Not necessarily. If we're looking for the first occurrence, we keep searching to the left of the position where we found the target. It's kind of like we're pushing that search window as far left as possible while still making sure we haven't missed any other occurrences of the target.
Ah, okay, so you keep narrowing it down until you hit the very first instance, and for the last occurrence, you do the opposite.
You got it. For the last one, we search to the right, pushing that window as far right as we can.
So it's like finding the bookends for all the instances of our target value in the array. Now, problem 35 caught my eye, finding the insertion position for a new element. Why is that so important?
Think about what happens when you need to add new data to a list that's already sorted. If you just tack it on at the end, the list isn't sorted anymore, and you lose all the benefits of using binary search in the first place.
Right, you got to figure out exactly where the new data should go to keep everything in order, but how does binary search help with that?
It all comes down to those start and end pointers we were talking about. As the binary search narrows down the search space, those pointers will eventually point to the exact spot where that new element needs to go.
So even if the exact target value isn't in the list, the binary search can still tell you where it should go to keep everything sorted.
Exactly. We just have to be a little careful about those edge cases. Like, what if the new element is smaller than everything else or bigger than everything else?
Right, got to think about those. So it's like finding the perfect spot on your bookshelf to add a new book so your whole collection stays in alphabetical order.
I like that. Now, earlier you mentioned something about finding a peak element in an array.
Yeah, I remember banging my head against that one in a coding challenge once. How does binary search even apply to finding a peak, which is like a value that's bigger than its neighbors?
It's a bit more subtle, but problem 162 shows how it's done. Remember, binary search works because the data is sorted. In a sorted array, the peak is always going to be at a spot where the values switch from increasing to decreasing.
So if you think of the array like a mountain range, the peak is the highest point, where the slope changes direction.
Exactly. By comparing the middle element with its neighbors, we can tell which way the slope is going uphill or downhill. That tells us if the peak is to the left or to the right, and we adjust our search range accordingly.
Ah, I see. It's like a hiker using their knowledge of the terrain to find the summit without wasting any steps.
Perfect analogy. We've seen how adaptable binary search is for arrays, but I'm curious to hear more about real-world applications. We talked about coding interviews, but where else does this actually make a difference in everyday life?
That's what I'm really excited about. In the notes, it mentions software development, game development, and network routing. But I gotta admit, it's hard to picture how those connect to things I do on a daily basis.
Okay, well, let's start with software development. Think about any time you've searched for something on a website or use that autocomplete feature.
Okay, yeah, I do that all the time. But where does binary search come in?
Behind the scenes, a lot of those websites and apps are using databases to store tons and tons of information. When you type in a search or start typing a word, the system needs to find that relevant data really fast.
And that's where binary search comes in.
Bingo. By using binary search on a sorted database, these systems can give you search results or suggestions crazy fast, even when they're dealing with millions or billions of data points.
So every time I search on Google, there's a good chance binary search is happening.
Very likely. It's also really important for keeping those databases organized. Remember how we talked about finding the insertion position for a new element? Same logic applies here, making sure new data gets added in a way that keeps everything sorted.
So it's not just about finding stuff, it's about organizing it in a way that makes future searches fast too.
Exactly. And this idea also shows up in game development. Imagine a strategy game where you need to choose the best move out of a ton of possibilities. Binary search can help the game's engine quickly evaluate those options and choose the best one based on a set of criteria.
Wow, never thought of that. So it's not just searching for things, it's about making decisions fast too.
Exactly. And then there's network routing, which is like how data travels around the internet. Binary search can help routers quickly decide the best path for data packets to take. Instead of just trying different routes randomly, they can use binary search to efficiently navigate through the network.
So it's like having a GPS that instantly knows the fastest way to get somewhere without having to check every single road.
You got it. And this speed is super important when you think about how much data is constantly flowing through the internet.
This is incredible. I had no clue binary search was so widespread. It's like a secret engine that's powering so much of what we do online.
And we've barely scratched the surface. There are so many more real-world examples and variations to explore, but I think this is a good spot to take a break for now.
I agree. This deep dive has already been a huge eye-opener. Definitely ready for more, though. Okay, so welcome back to our binary search deep dive. We've covered so much, from the basics of how it works to, some pretty clever variations and everything.
Yeah, and we've seen that it's not just some theory, but it's actually this super useful tool that pops up in all sorts of places, like software development and game design, even like network routing.
I have to admit, before we started this whole deep dive, I would never guessed binary search was so widespread, but now I'm starting to see it everywhere.
It's like this hidden gem of computer science. And in this last part, I really want to make sure you walk away not just knowing how it works, but also understanding why it matters so much in the real world. So let's revisit some of those examples and really break them down,
Yeah, sounds good to me. Last time we left off talking about network routing, which is, how data travels around the internet. It's still kind of mind-boggling to me how binary search fits into something as massive and complex as the internet.
It's all about making smart choices and making them fast. Think of those routers like traffic cops directing data packets down the best path. Now imagine those routers had to just randomly try different routes until they found the right one. It would be like total chaos.
Yeah, that would definitely slow things down. So how does binary search actually help those routers make decisions faster?
So the internet is actually structured in like a hierarchy, kind of like a family tree. Routers use this hierarchy, along with information about, network traffic and stuff, to maintain sorted lists of the best paths to different destinations.
So it's like a map that tells the routers the most efficient route, and it's constantly being updated.
Exactly. And when a data packet comes to a router, The router can use binary search to quickly zoom in on the best path from that sorted list without having to check every single option.
So efficient, like having a GPS that just always knows the fastest route, even with traffic.
Exactly. And this efficiency is super important because remember, we're talking about billions and billions of data packets zipping around the internet every second. Without algorithms like binary search, things would just completely grind to a halt.
Okay, yeah, that makes the impact super clear. So let's shift gears to databases for a minute. You mentioned that websites like Google and Amazon use binary search to handle huge amounts of data. Can you give me like a specific example of how that actually works?
Sure, let's take Google search. When you type something into Google, it needs to sort through like billions of web pages to find the best results for you. Imagine if they had to check each page one by one. It would take forever.
Yeah, I'd probably just give up and go to a different search engine. So how does binary search help?
Well, Google indexes those web pages and stores information about them in this massive database that's, sorted. This includes things like keywords, links, and other stuff that helps determine if a page is relevant to what you're searching for.
So basically, when I search for something on Google, it's doing a binary search on that giant sorted database of web pages.
Yep, that's how they narrow down the possibilities so fast, even with billions of entries. That's why those search results pop up in, like, less than a second.
It's crazy to think about all the work that happens behind the scenes just to give us those instant results. And you know what? It's not just about speed either. It's also about accuracy.
Oh, absolutely. Binary search makes sure that the most relevant results come up first, based on how everything's sorted in the database. That means you're more likely to find exactly what you need on that first page of results instead of clicking through pages and pages of useless stuff.
So it's not just finding a needle in a haystack, it's making sure that the most important needles are right there at the top.
Exactly. And this applies to other things too, like autocomplete. As you type, the system's constantly doing these binary searches on a sorted list of words and phrases, trying to predict what you're going to type next.
So binary search is even helping me write emails and texts faster and more accurately.
You got it. It's all about using the power of sorted data to make those everyday things we do online way more efficient. And honestly, it's not even limited to the digital world. Think about any time in real life where you have a sorted list of things, like a phone book or a dictionary.
Are you saying I could use binary search to find a book in the library faster?
Totally.
Yeah.
Instead of going through the card catalog one by one, you could do a mental binary search to zoom in on the right section.
That's insane. I never thought of applying a computer science algorithm to, like, real life.
That's the cool thing about it. These algorithms aren't just abstract ideas. They're actually powerful tools that can help us solve problems and make things more efficient, both in the digital world and in our everyday lives.
Wow, this deep dive has completely changed how I think about binary search. It's not just for programmers, it's something that impacts all of us all the time.
And I hope it's given you a new appreciation for those hidden algorithms that make our world work.
There's so much going on behind the scenes. It's just fascinating to understand how it all works. I couldn't agree more. And who knows what other awesome algorithms are out there just waiting for us to discover them. Thanks for joining us on this deep dive, and we'll catch you next time.